First talk will be, first speaker will be Renzo. His topic is Vortex Reconnection in classical and quantum systems. So Renzo, your turn.
Okay, thank you very much. So in these 40 minutes, my intention is to cover some basic aspects of reconnection, just to help the junior people to get acquainted with this mechanism that is very important. And then I will focus on aspects of helicity, of course, reminding you linking writhe and twist. I'll consider writhe conservation under anti-parallel reconnection, that is a result that we derived a few years back, and then the helicity change in terms of twist transfer in particular. Then I'll consider zero helicity and total twist conservation for quantum defects, and I'll mention aspects related to the evolution of isophase surfaces through reconnection. That is a theme that we started considering in the last few years. The first thing I'd like to show you is go to this movie very quickly, just to show you very beautiful experiment by Lim long time ago, 92. That has never been repeated. You will see collision of two head-on vortex rings, and the collision will generate this diadema of little vortex rings, that ringlets, so to speak, that will be formed. So let me show you. One is red, and so the ringlets inherit a part of the blue and part of the red. And this is a remarkable result done in water. A vortex is formed again in water, and the three-dimensional visualization of this vortex filament should convince you that this is actually a trefoil. Then there is an evolution taking place, and so there are two rings, two Hopf-Ling rings linked together one another, barely visible. And then a further reconnection takes place, more or less here. And the production of, well, before final dissipation, the production of two unlinked vortices disappear quickly because of dissipation. So these are systems that display dissipative systems that display these reconnection mechanisms in a very great detail, although because these filaments are very thin, we cannot see much of twist in these systems. And this is the movie, so please tell me when you can see that.
Yes, we can see that.
I will discuss briefly what you see here. The focus is on twist this time, and okay, very good. So you see here approaching a helical vortex. This is a helical of this work, extremely interesting. And as I proceed with evolution, piece of helix become anti-parallel. And you see here the twist, the relative twist. And then there is a merging. And there is, as you can see here, there is a thread of vorticity still visible by the little bubbles that are somehow sucked by the low pressure field. Here again, we see they approach and then they turn one around near the other to become anti-parallel. And then they merge, they leave each other with this thread of vorticity. Okay, so we have the two rings. I just speed up a little bit. So you see we have two rings, and discretization, because we were just keen to reproduce a limb as say a first order approach, so to speak, in order to understand if under GPE, here we are under GPE, if we could see the same things. And indeed, as the two rings approach, again, remember, they approach according to one direction, then there is an instability forming, and then as the instability grows, there are reconnections taking place at various locations. And then, the ringlets, so to speak, form, and they separate off from the plane of collision. Simone simulations of 2012 is a very famous paper where you can see again the reconnection starting from perpendicular to become anti-parallel in this particular case, and reconnections goes on. So this is actually something that has been noted since the 80s, and is reassuring that the same thing happens for GPs. So I can just explain you the mechanics of this vortex reconnection starting from Biot induction law. If we develop an asymptotic theory, as you can find even in Darius 1905, but certainly in Bachelor book 1967, 7th chapter on vortex dynamics, you see the term due to an azimuthal, a rotational flow around the axis of the vortex, and then a binormal flow. So this is plus finite terms of contributions. This is, remember, an asymptotic theory. So we are very, very close to the vortex filament. And remember, you have two contributions, one due to azimuthal circulation and the other one due to the binormal circulation. Here is a screenshot from the Alexienko evolution, and you see a tangent along the axis, and then the normal along the curvature, and the principal curvature, and then binormal along the second principal curvature. And this is the induced motion by vorticity, a motion, a circulatory motion. If the vortex is straight, we have only the circulatory motion. If the vortex is bent, we have a secondary motion due to the binormal component. Now, I want to focus first on this azimuthal contribution only. If the vortices are along a parallel direction oriented the same way, then circulation is oriented in the same direction, and we have a circulatory flow around the two vortex filament along, like shown in this diagram. Now, by numerical simulations and by experiments, we know that there is a merging of these two parallel filaments into one big filament. And this is one of the many simulations, one of the last simulations done by Maurice Rossi and Jacques Josserand in Paris. Well, what about if we have anti-parallel vorticity? So if we have anti-parallel, the two circulatory motions are squeezed at the center. And now we want to focus on this central region. Remember, we are just focusing on the azimuthal contribution only. So if we focus at the center here, we have a sum of these azimuthal contribution in this fashion, of course. And so P, the point of symmetry, is the point we care about if we want to consider the velocity induced by the two components, the azimuthal and the binormal. So if we consider the anti-parallel configuration by applying Bernoulli's theorem, I want to focus here on the fact that even in an ideal situation, of course, in my mind, we want to care about viscous reconnection, but even in ideal situation, we can easily prove that vortices become anti-parallel. How? Well, we apply Bernoulli's theorem on this point P, and Bernoulli's theorem says that the pressure at the point P plus the contribution of kinetic energy density is a constant at that point. And a little bit of geometry here will convince you that because the velocity at P is given by the two azimuthal contributions only, because the binormal contribution UB1 and UB2 annihilate, they cancel out each other. So this is 0. We are left with these azimuthal contributions. And by elementary arithmetics, you can see that we have 1 plus cos alpha coming out. So if alpha is 0, in other words, if they are anti-parallel, we have a maximum of this velocity, and that means because of the constancy with the pressure, we have a minimum of the pressure. And the minimum pressure is what drives together these vortices. This elementary, well, I call it a proof, but is just an elementary consideration. This elementary consideration is missing in literature, and I like to share it with you as part of what I teach to students in my master class. So this Renzo, is just, Renzo, yes, go ahead.
Renzo, may I raise a question?
Yes.
I'm not sure if my understanding is correct. So your meaning is, for example, at the beginning, the red arrow and the blue arrow, they are not parallel or anti-parallel to each other. But
that's
the
right.
Bernoulli theorem will just drive these two guys to be anti-parallel. You just give
that's right.
Yeah.
Yes, so, that is correct. Exactly. That is correct. Remember, for the junior members, you should remember that there is a viscous process going on. So this is just a very simple elementary discussion of the process in absence of viscosity. So there are lots of issues coming in the problem, but you can see even at the elementary level, I discussed this, you can easily see that to optimize the process, in other words, to get to this low pressure region at the center, you need to have antiparallel reconnection. Okay, well, observation of antiparallel reconnection abound in many cases, as you saw in real vortex reconnection, in simulations, as is shown here. And this simulation 2011 already is very visible, this thread of surviving weak vorticity left out after the process. Well, helicity, I will focus on helicity. Remember that this is an invariant in ideal fluid mechanics, and you all know this decomposition in terms of self-linking and Gauss linking number. I will be very quick here, just to remind you that Gauss linking number is a measure of the linkage between different components, and the self-linking number is just the topological invariant due to Kalugareanu and extended by White in a higher dimension as a sum of the writhe and twist. And remember, this self-linkage must be constructed on a ribbon concept. As the line chi is not enough. The line chi has to have a physical neighborhood. In other words, we have to talk about physics here. The physical structure around the chi line allows us to construct a ribbon R, and through this ribbon R, we can construct these invariants. Writhe measure coiling, and there is a sense of torsion in the line as well, the central line, and the ribbon is just the combination of total torsion and intrinsic twist that is visualized here by this straight ribbon. Okay, so if we consider the reconnection as from one of the screenshots shown in the experiment by Irvine, we can guess that what we call the projected writhe is nearly 1 all the time across the reconnection. Remember, writhe changes with evolution, but just before the reconnection and after the reconnection, there is a sense here that the projected writhe may be conserved. Indeed, we can prove it rigorously if we assume that from continuous description we go to a discrete polygonal version of these curves. This is a standard technique in topology, and we can play around with these polygonal curves so to move rigidly one curve against the other in anti-parallel configuration. So a sketch of the proof is made of 2 steps, and the first step is pretty important as well. So let A be an oriented n-edge polygon with all these edges equal, and B another oriented m-edge polygon with all these edges equal. Then the writhe can be constructed from the spherical area interpretation of the writhe as the double sums of these spherical surfaces contributions, and the linking as well admits this interpretation. This is very well known. And if we consider the writhe of the before stage of the union of these disconnected components, we can see that by just careful analysis, we can see that there is a contribution from these AIAJ and BIBJ that contributes to the writhe of A and the writhe of B. But then we have a contribution from these edges AIBJ and BJAI. In other words, the linking numbers between these 2 quantities. So we can come up with this formula. This is a very important formula. The writhe of the union of these 2 curves is given by the writhe of the first curve, the writhe of the second curve, plus twice the linking number between these 2 curves. So we will use this result in a moment to prove the following, that the writhe of 2 disjoint-oriented polygonal curves A and B is conserved under antiparallel reconnection of A and B. In other words, the writhe of the disjoint union is equal to the writhe of the connected sum of these curves. And the proof is extremely simple once you rely on this polygonal description and the Gauss map consideration. You consider these 2 curves, and then you consider antiparallel configuration, and then you do a rigid transport of this curve against the other. The rigid translation of these 2 curves does not change writhe or linking, and then because these 2 edges are oppositely oriented, they cancel out in the spherical area consideration of linking number. So you can prove that the writhe of a disconnected component is equal to the writhe of this intermediate stage, the connected, the components when they are superposed. If we are at this stage, then by spherical area consideration, you can show that these 2 oppositely oriented edges cancel out from the spherical area interpretation, and so you can prove that these 2 stages have same writhe. And that is basically the proof that the writhe of the disconnected components is equal to the writhe of the connected after components. If 2 vortex tubes of axes A and B have the same circulation, then the writhe helicity is conserved under antiparallel reconnection, because you pass from polygonal curves to continuous curves, and then you are there. So this is an easy step. Now, remember, I mentioned that we deal with real physical systems. So in case of a dissipative system in classical vortex dynamics, we have 3 contributions. One is the production of helicity density. The other one is diffusion through viscosity of helicity density. And the third is dissipation, again, due to viscosity and this quantity omega, the vorticity, dotted with the cross of the vorticity. So this is called superhelicity in certain circuits. I'm happy to show you a very recent result I got from Hussein simulation. This is a piece of work that I believe has been submitted to JFM very recently, and this is a collaboration with Yao and Yang from Peking and Fazil Hussein in Texas. And this is a very beautiful set of pictures that shows you how the helicity density changes with time and how helicity dissipation in particular is localized during the process. Here we start with the trefoil knot, and you can see now the stage where the trefoil gets reconnected at three instantaneous symmetric points, because they start with a very symmetric configuration. And as the reconnection process, as it goes on, you see a secondary structure forming, a ring structure forming from the rest. So we have a large ring behind and a small ring on top that is, because it's smaller, has a higher curvature radius, it will leave the structure behind, the larger ring behind quickly. So you can see how these things go, and the threads of weak vorticity behind. So I believe this is a piece of work that has been submitted to JFM, and we'll probably enjoy its reading shortly. Okay, in the case we have a change in helicity, as we had here in presence of dissipation, we have a change in twist, because Rife, as I mentioned, remains conserved. And so the helicity change is purely due after reconnection to this change in twist. Now remember, twist is made of two contributions. One is total torsion and the other is intrinsic twist. However, under antiparallel reconnection of two flux tube, twist is conserved. Then if antiparallel reconnection takes place and the twist is conserved, helicity is conserved. That is obvious. But since under antiparallel reconnection, two flux tube, torsion is additive, because torsion is additive, we have that a change in helicity is purely ascribed to intrinsic twist. And this is something that people should become aware of. And this is a result that was stated in our work with Dewitt Sumners and Christian Lang. In case we consider Berger's vortex, Berger's vortex is again something I teach in my masterclass, is an exact solution of Navier-Stokes equations. So we have viscous dissipation again. Then we can state that the change in helicity is actually, because of change of twist, is actually due to the change of intrinsic twist only. And this is the equation that we derive from Berger's vortex. This is the equation that governs across reconnection, the change in intrinsic twist. And by further analysis, we see from literature that this can be also related to the change in circulation, where UZ1 and UZ2 represent the axial flows of these two reconnecting tubes. Let me consider now GPE evolution. Now, I have to correct a wrong statement by Matteo in the last session of our meeting. The idea to use the isophase surface here, visualized in red, to construct a ribbon is actually not new, goes back to our work. Simone's in particular use it to construct the ribbon, so is not new. And we can follow the isophase surfaces during reconnection. Now I want to switch back, if I can, to show you my last movie. So let me, bear with me, be patient. I will just go to a new share and tell me when you can see my screen and the movie. So this is the evolution of an isophase surface of a Hopf and myself in 2017. Please let me know when you
can
see the screen.
Yes, we can see that.
And when the evolution will. Okay, very well. So you see here, we start. Okay, good. We see an initial configuration given by a ring and another ring. The two rings are linked together, and we want to follow this isophase evolution. So I show you this movie in particular to show Shin about the evolution of this surface just across a twist of this surface. You see here, there is a first reconnection taking place here, and then a second here. And now I will slow down or eventually stop when the two strands reconnect. Remember, this is a twisted surface, apparently, and the reconnection will take place here, the first one. But if you imagine to change your viewpoint direction, you will see that now we are approaching the reconnection. You will see that there is no twist of this surface here. No twist of the surface. Okay, now you're very close to reconnect to say, oh, sorry, here. The reconnection, you see the reconnection, first reconnection takes place here. And there is a second reconnection that will eventually take place here. Now from, okay, and then further reconnections eventually for a further ring down there. So let me go back. You see very visibly that the surface here is not at all twisted, it's just merging one another. And here also is merging one another. Okay, I go back to my presentation now, if I can. Just to, I will close this last movie. Sorry for this, I'm slow with this. Okay, just a second. All right, almost there. Okay, you should see my presentation again in a moment. Please let me know if you see it. Anyway,
yes,
by taking care, okay, by taking care, we could follow how twist recombines during reconnections, etc., etc. This is again a paper of 2017. In the case of zero helicity for GPE, this is the situation. If L is the disjoint defects, the isophase surfaces determine oriented Zipher surfaces, which are bounded by the defects. And as pointed out back in 92, and more recently by Haider Salman in 2017, helicity for, and Here, Marcus White, we can rigorously, again, by topology. So this is quickly the result. If L has a cipher framing, then the helicity of the whole system is 0, where helicity of each component is given by the self-linking number plus the linking of this component AI with the other component AJ, and the cipher framing is conserved under antiparallel reconnection. And this is evident from the simulation that I just showed you. The theorem goes, the total twist of two cipher-framed defect A1 and A2 is also conserved under antiparallel reconnection. That is, the twist of the first and the twist of the second sum up to the twist of the reconnected sum. Okay, I'm concluding by showing you some last piece of work that Simone and I did. This was done with the old code, and so this is the showing you the time evolution of the isophase surface of least area done with different computational grids, and you see now the isophase, the minimal isophase, keep decreasing as the evolution goes on through reconnection. Same thing happens remarkably in the case of several knot types. So let me conclude, since I'm at the end of my contribution, with some open questions that I'd like to address in the coming months or years. You observed from numerical work the contribution of two head-on collisions of rings under GPE. If we reverse the simulation and we make these rings colliding to the center, in other words, we reverse the result of the collision of GPE, the area, the minimal area, increases rather than decreasing. So we evidently have here a puzzle. Which one is the correct one? If we follow the limb simulation, the area will decrease. But what about if we make vortex ring colliding one another? We know from simulations with Simone that the area actually increases. So the puzzle here is what about a monotonic decreasing fashion of this area, which I believe in reality will take place. The second question for everybody is, what is the energy and the minimal surface relation? Energy is given by several contributions, and the preliminary check by Simone on these contributions make us believe that some of these components are far more important than others. And so we like to understand the relation in terms of energy of this eventual minimal energy evolution. And the third question is far more difficult, and is a question to Shin in particular, and is the following. Is the minimal surface evolution, if confirmed, a critical geodesic by mean curvature flow in the knot polynomial space? Because remember, we saw the same thing happening for several knot types, and we know that this is also true for Hopf-Link. So we know that if we allow one reconnection at a time, we know from the work we did with Shin and with Xin-Fei Li that in the knot polynomial space, we have geodesics governing this topological cascade. So I wonder if the minimal surface evolution is a critical geodesic among the many by mean curvature flow. So I stop here and I thank you very much for your attention.
Okay, thank you so much, Renzo. Yes, you just give us a very interesting and inspiring